The next hypothesis test we're going to look at is a two-sample pooled t-test. So what we're doing is we're comparing our means between two groups. So we have two samples representing two groups within the population. And we're going to look at what is called a two-sample pooled t-test and a two-sample separate variance t-test. The difference between these two is the assumption we're making about the variability in the population. So in a two-sample z-test, we knew the standard deviation or variance in the two groups in the population. A t-test, we don't know the standard deviation or variance within the population. So you can make an assumption that the two groups have similar variability. That would be this test. Or you can make the assumption that the two groups in the population have different variability, in which case it's a separate variance t-test we'll look at in our next video. So we can look at the variability in our sample and try to extrapolate about what's happening in the population, and we'll do that in just a moment. But we're using a t-test because we don't know what that variability is. So let's talk about how a two-sample pooled t-test works. So our null hypothesis is going to contain two mu's, two means for the population, just like with the two-sample z-test. And here we have the mean of group 1 minus the mean of group 2 is equal to some number. It can be equal to 0. It could be equal, you think there's a difference of 5. So the alternative hypothesis then is going to be the opposite. So if the null hypothesis is that the difference is equal to 0, the alternative hypothesis is that they're not equal to 0. The difference is not equal to 0, meaning they are different. So often when you do these two sample tests, you're not looking at actually a number, like the difference being 5 or the difference being 2. You're often looking at, is there a difference or no difference? But you can actually do the test to say, okay, is the difference equal to 5 or not equal to 5? Is the difference greater than 20? And so you can have a number there. So our test statistic is going to be t equals, and then we have x bar 1 minus x bar 2. So we have the difference between the two sample means minus whatever we're proposing in our hypothesis is that difference. And then what we have at the bottom of our formula here is a pooled variance for the two samples. So if we're saying they have equal variability, we could then look at the overall variability of the samples combined, not treating them separately. And then we have 1 divided by n1 plus 1 divided by n2 in the square root. Now the degrees of freedom in this test are going to be n1, the size of the one sample, plus the size of the second sample, minus 2. Remember in our t-test, our one sample t-test, it was the size of the sample minus 1 because we had this other sample statistic inside of our test statistic. And so here, because we have two samples with both of an average and the standard deviations, which are unknown, are going to be related to those averages, then we're subtracting 2 to get the degrees of freedom. So here we have our test statistic and we have our calculation for pooling that variability. The assumptions for this test: random sampling, so our sample represents the population at large. We have an underlying normal distribution. The population variances or standard deviations are not known but assumed to be equal. And the samples are independent. What we mean by an independent sample is that the people or entities who are in group 1 are not the same people or entities that are in group 2. So an independent sample, different people in the two different groups. Dependent samples, so we'll look at a paired t-test in the upcoming video, is where the same people are in both samples. So this would be where we would do like a pre and a post test. So we would assess you before some kind of treatment and we assess you afterwards. So the same people are compared across time when we have dependent samples. But right now we have independent samples. Okay, so is the population variance really equal? If we were to test for equal variance first, then we have dependency between our tests. And this will increase the significance level of the second test. Because your two tests depend on each other, then what happens is the error compounds. So if the significance is 0.05 on a test for equal variance, then the significance on the pooled t-test is approximately 0.01. Okay. So there is this relationship between tests that we have to recognize impacts the accuracy. Now, the test for equal variances has its own here set of hypotheses, where we're basically saying our null hypothesis is that the variances are equal, the alternative hypothesis is that they're not equal. And we can use an F-test, which takes the standard deviation squared, so the variance of our two sample statistics, and divides them in that calculation. Use a different distribution table. It has its own set of assumptions: random sampling, normality, and independent samples. And it can, of course, can have its own confidence intervals as well. And I'll show you how, when we get to Python, how to do this test in terms of equal variance. Okay. Now, going back then to the main test, this pooled t-test, we can create confidence intervals for it. You'll notice those confidence intervals are just rearranging that test statistic, just like you've seen with all the other confidence intervals so far. So they can be two-tailed if we have a two-tailed hypothesis test, or one-tailed confidence intervals can go with your one-tailed tests. All right, let's take a look at an example. A college dean believes that car ownership among students leads to lower grades. To test this hypothesis, she obtained a random sample of student car owners and non-owners and looked up their grades. So if we go into our data set here, we have under the GPA tab, let's just make this bigger so we can see it. We have here students who own a car, students who don't own a car, and we are then going to do a pooled t-test to compare those two groups. If you are doing this in Excel, then you will need the Data Analysis Tool Pak. So once more, if you are on a Mac, you can go to the Tools menu at the very top, and you can add the Excel Add-ons Analysis Tool Pak. If you are on a Windows computer, you will have to the left of this Home tab, you'll have another tab here, and you can go to Options, Add-on, and install this Data Analysis Tool Pak. In the Data Analysis Tool Pak, you will see that we have a two-sample t-test assuming equal variances and a two-sample assuming unequal variances. So this equal variances is that pooled t-test. The unequal is the separate variance we're going to do next. Okay. All right. So in order to do a two-sample equal variance test, you will need to identify the data. So variable 1 is going to be those who own a car, and variable 2 is going to be those who don't own a car. And then we want the hypothesized mean difference. And in this particular case, what are we hypothesizing? So I'm just going to leave this temporarily and let's go back because we need to make sure we write out all of our information. All right, null and alternative hypothesis. A college dean believed the car ownership among students leads to lower grades. So here we have mu1, so let's call that car ownership, and minus mu no car. And what we believe is that car minus no car leads to lower grades. So if car is lower than no car, this is going to be less than 0. Okay, and that means the null hypothesis is going to be greater than or equal to 0. We need an alpha, so what is the significance level? Maybe we're going to do 0.05 here. Okay, and we need our test statistic. So our test statistic is we're doing a pooled t-test. Okay, and the assumptions that go with that t-test, which is that we have a random sample, that we have normally distributed underlying population, that the variances in the population of the two groups is unknown but is equal. And the last one here that we have independent samples. Then we're going to create our decision rule here. In this case, we are looking at that car minus don't own a car is going to be less than 0. So we have a left-tailed test. We're putting all the 0.05 into the left. We have our critical value here, and we are going to then reject the null hypothesis if our test statistic is less than the critical value or our p-value is less than alpha. Okay. All right, so let's go back to our Excel. Data analysis. 2 samples, assuming equal variance. Variable 1, those who own the car. Variable 2, those who don't own the car. Difference we're assuming is 0. We're doing an alpha of 0.05. You could choose instead a 0.01. Okay, all right. Conduct the test for us. So what we have here, which you can't see because that's super tiny, so let me make that bigger, is that our degrees of freedom are 34. Our t statistic here is negative 4.389. And so if we're looking here, negative 4.389, we would compare that to our critical value. Now, we could look up that critical value on a t distribution, but we can also just go here where we have the information in terms of our p-values. So here we have the probability that our critical value is less than or equal to t. So here's the one-tailed test, and here's the two-tailed test. We have a one-tailed test, and so when we look at our one-tailed test, the t critical value is, if it was a greater than, it'd be a positive 1.69, but it's a negative 1.69 because it's a left-tailed test. And we compare that negative 1.69 to our test statistic of negative 4.39, which is way out here. So we come back, we reject the null hypothesis if the test statistic, this number, is less than the critical value 1.69, which it is. So we reject the null hypothesis. We also reject the null hypothesis if the p-value is less than alpha. So when you look at Excel here, our p-value for the one-tailed test, notice that it's 5.23 e to the negative 0.05. This is engineering notation. It means that you can add a bunch of zeros in front of this 5. So the negative right here means that this is actually 0.00005. So we're actually moving the decimal place 5 places from behind the 5 to up here where we then have 4 zeros and a 5. So that number is very, very, very tiny. So if you have an E with a negative number, that means this number is very small probability. We're comparing this number to an alpha of 0.05. Well, 0.05 is much bigger than this p-value. If the p-value is less than alpha, then we reject the null hypothesis. So in this case, we're going to reject the null hypothesis, and we see those who own a car have lower GPA than those who don't. Okay. Now, if this part is tripping you up, what I often do is write it this way. Those who own a car are less than those who don't own a car. And then what you should do is then subtract whatever's on the right. Keep your greater than or less than sign the same way and then put a 0 there. So you're simply, if this the way makes sense to you in your mind, write it this way and then move this over by subtracting it from both sides. Okay? So in this case, we're rejecting the null hypothesis. Those who own a car have a lower GPA than those who don't. Okay? And we got that in Excel using our 2-sample equal variance. All right. let's do this in Python. So just a reminder, we are at drstephpowers.github.io/BIA. We are working through the supplemental materials. Click on hypothesis testing. What is this? And go away. Oh, I don't even know what I clicked on. There we go. Come back. When you click on that, sorry, there's some weird thing showing up on my screen that you can't see. That's confusing me. Okay, so when you go to drstephpowers.github.io/BIA, you click on hypothesis tests. Then what you do is click here on Open in Collab. This opens in Google Drive. Make sure you're logged into your Google account. Make sure you save a copy in your drive. You will also need here the data sets, and you can find the data sets here under Data. We are using Statistics and Statistics 2. And so use those by downloading them. So click on that, download it here. Make that a little higher. Download this and then dump these two into your Google Drive. Once you are in Google Drive, I'll just start over here. Once you're in your Google Drive, you will then need to import pandas as PD, import numpy as NP. We need these in order to import our data and manipulate it. You'll want to make sure you mount your drive. So this connects your workbook to your files in your Google Drive so that you can import the files. It doesn't give access to anybody else. So we are down here under pooled t-test, and I am importing from statistics.xls the sheet name GPA, and for me, I have put that file in a folder called appendix that's inside another folder called BIBA handbook. So specify where it's located so that you can import it. So I'm just going to call this dataset X5 as I bring it in. Always a good idea to see what it looks like. This one, as you notice, the Excel that it was originally in was kind of weird because it has students 1 through 18 and then own a car and then a column space and then students 19 through 36 that don't own a car. So when I import it in, we get this empty column. We don't have to deal with that. We can ignore that here simply because we're going to tell it to pull this column called own a car and this column called don't own a car. Now, one thing that's important to note, notice I have no apostrophe here. If my original Excel file had an apostrophe here, when I would go to do things to call that variable, then Python would get angry and not do what I want it to do. So make sure that the names of your variables don't have any apostrophes in them. Okay, so I just got rid of it. It says don't own a car, no apostrophe. Okay, so data is now in. Then in order to do our test, we are going to use skippy.stats and we're going to do a independent t-test. So we're going to import t-test underscore independent. Now, when we do this t-test independent, we will specify that we are comparing. The first group is own the car. So from the data set X5, the variable own the car. And the second one is going to be X5. From X5, don't own a car. Again, no apostrophe there. And then we're going to do equal variance equals true. So we're assuming they have equal variability. And the alternative here is less. The alternative is that own a car is less than don't own a car. Okay. Now, I can run this test just like we did in Excel. I get a test statistic of negative 4.389, which should look very familiar. Right? Negative 4.389 was our test statistic. And our p-value was super duper small. And we can see inside here, we get a very small p-value as well. Now, one of the things we said about the pooled t-test is that it assumes equal variability in the two samples. So the two lines of code I have right here are a test using the Bartlett test to see if there is equal variance. And so we'll just go back to our notes for a second, where we had this short divergence. And you see how we had that the null hypothesis is that they are equal in their variability, and the alternative hypothesis is that they are not equal. So the test here is sigma 1 squared equals sigma 2 squared. The alternative is that they are not equal. So essentially we're doing another hypothesis test, right? We could set an alpha here of 0.05. Remember, if we do that, if we put a 0.05 for our variance test, then really we need to be comparing to 0.01 in our pooled t-test. And we could then do our test here, just like with any other test. Here's 0.025, here's 0.025. And instead we have F values. It's not technically correct because it's not a normal distribution. So maybe I won't put that to confuse us because the F distribution is not a normal distribution. But we can use the same process, which is we will reject, reject H naught if the p-value is less than alpha. Okay. All right. So let's take a look. In Google, in Python, we can import the Bartlett test from skippy.stats. So let's call in from skippy.stats, import Bartlett. And then we'll use the Bartlett test and we'll apply it to our sample from dataset X5, the column called own car, and from sample X5, the variable called don't own a car. And we can run this test. We get a sample statistic of 0.41. We would compare this to an F critical value. But we can just look here at this p-value of 0.5. Well, our p-value is 0.5. It is bigger than our alpha divided by 2. And so if the p-value is less than alpha, we would reject the null hypothesis. Our p-value is not less than alpha. Our p-value is quite big. And so it is quite possible that the null hypothesis is correct, or else we just can't detect the difference. So here we have done a test to show that the variances are equal. Okay, so you can do the Bartlett test to test your assumption here that your variability in your two groups in your population are equal. Just recognize that if you're testing that, your two tests are actually dependent on each other. The results of one impact the results of the other. And so it's actually impacting the overall significance of the second test. So if you do a 0.05 on the first test, then the significance level you're using on the second test is 0.01. Okay. Before we leave this, I'm just going to point you to, but I won't do it. I have for you here a second data set called economics, and it looks at, let's go back to the original data here, somewhere. All right, scores. Test scores for introductory economics classes given in the evening and the afternoon. If we assume the variability for the grades in the evening class are similar to the variability for the grades in the afternoon class, use a 5% level of significance. Does the class seem to perform better on average? Does the evening class seem to perform better on average than the afternoon class? So can you create a null and alternative hypothesis and then perform this test in Excel, perform this test in Google, in our Python code in Google Colab? And so we do have here for you, import that table and run that. So same code as you did before. You can even test the variability. Can you answer the question of, using a 5% level of significance, does the evening class perform better on average than the afternoon class?